All right. Okay. Hi, everyone. Thanks for coming to the Wolfram Live R&D session. My name is Shenghui Yang. I work for Wolfram Alpha team, and I would like to solve challenging math problems during the work time and off the work time, because I really like those interesting problems, and you can find on internet. And I have done a couple of the problem-solving sessions during Wolfram conference, and most of them are already on YouTube. So you can just find the Wolfram technology channel and find those problem-solving sessions if you are interested in those challenging problem-solving techniques and how to use Wolfram language and other resources to help you understand the solutions and promote your understanding of what's behind and the background of those problems. Okay, so today I'm going to first introduce why I'm going to give such type of lectures and online session or conference talks, because I found recently, everything get more competitive during the industry, in the industry and in the education system. Okay, so students or other math enthusiasts, they will find the things they learned before probably is not good enough for them to understand the harder problems, or practically speaking, get them into elite schools or programs, because they need to deal with harder problems to pass the selection process. And there are many problems will be available in all kinds of online resources and the summer school problem across the world. Some of them are really challenging and selective. For example, like AIME, AIME, PROMYS, and SUMAC are very popular programs that students all over the world are very interested, including Wolfram Summer School. So there are many harder problems they want to solve, and eventually you will get, for example, like AIME, you need to get a top 2.5% to be top 2.5% in the AMC 10 to be selected as student that you can participate in AIME. And after that, you will be need to complete lots of hard problems so that you will be elected for USMO. Okay, so for those hard problems, including SUMAC problems, and the background you can check with Wolfram language in using Wikipedia data, and you will find the background of these programs. And they always give you very challenging and interesting problem to solve. So this, when you actually in the exam, you're like exam takers, and you can only do with a pencil, eraser, ruler, and compasses, just like what a mathematician does for 2,000 years ago. But I mean, if you can solve that with those rudimentary methods, that'd be great. But for lots of people, I feel like even the solution is just very hard to understand if you don't have any technology to support you. And this is basically the purpose of this type of session I'm making right now, because with the Wolfram technology, you can easily visualize. And because I'm a visual learner, and visualization great helps you to understand the problem. The other thing is, those programs like to give you problems from combinatorics, number theory, or discrete calculus. It's basically pioneered by Knuth, and he talks about lots of computer science related discrete calculus, discrete mathematics like combinatorics. But what's the difference is discrete calculus requires you to do some calculus related things, which I mean in higher math, it's take the limit, or you do things about asymptotics, which is covered greatly in the Wolfram language after version 12. And we have algebra and analysis for things that you can model by differential equation, basically. And then if you work with those problems and typically you read the solutions, one of the biggest problem is you don't know where the solution comes from. Because they usually prove either by contradiction or using constructive method to create a solution. And this solution usually looks like comes from nowhere. So I think using software, typically Wolfram language, greatly helps you to understand where these problems and typically the solutions come from. For example, in one of the community article I just released, it's talking about a simple problem, but involves derangement, pigeonhole principle, modular arithmetics, and cyclic permutations. It's something like it's a baby course in group theory. Okay, but these ideas and concepts are really abstract if you don't do any simulation or experiment to help you understand what's behind it. You need to also throw in a bunch of parameters that you can change so that you can see how these parameters change the solution and how it affects our solution seeking process. So I would like to just give you some of the examples during this talk. And these problems are selected from usually these very elite resources. So you can try to understand and read the code and play around with the problems and learn how you can come up with a solution by yourself. And this is very important because math, I think, is just like engineering or other experimental science. To some point, logic and sort of deduction is just not enough. So you need to work with some of the cases, typically with number theory, combinatorics, and these branches of mathematics. It's really hard to find a systematic way to solve all the problems. You just need to play around with some of the simple cases, and eventually you know what to do. And probably you find a result, and then you can link it to some online resources. Someone maybe already solved it, but it's just very difficult if you just want to describe them verbally. I'm going to show one of the problem like that in the session. Okay, so here are my previous talks. These all have YouTube links, so you can click that, or you can just check that. It's here. So if you have the notebook, you just click that, and you will be able to review the past problem-solving sessions on YouTube. Okay, now let's first start without further ado, let's start from a very fresh AIME problem this year. So let me just quickly explain what's going on here. So there are 5 men and 9 women sitting equally spaced around a circle in random order. So that means you have to sit on the points or the vertices of a regular polygon. So for example, there are 4 people, you must sit on a square. Okay, 5 people, you sit on the vertices of a pentagon. So you always, that's equally spaced means on the circle. So the probability, so basically we are going to find the probability where every man sits diametrically opposite to a woman. Okay, so the last part is basically the style of AIME. So you need to find a solution that's between from 000 to 999. You have to write 3 digits. So this is the type of the format of answer that's required in AIME. But eventually the problem just asks about the probability that every man sits diametrically opposite to a woman. Okay, let's see the simulation here. So assume men are red, ladies are blue. So these are the simulated results. Okay, and this also contribute. This after you learn this how you program this problem. This it will give you a huge boost in language the Wolfram language programming skill, because this is related to a very typical problem is generate a random permutation with restrictions. So without the restriction, you basically just randomly permute the dots on the circle. Okay, but my requirement is you can have blue to blue. Say you get 1/8 is blue to blue is diametric. Okay, but you cannot have red to red. So red must opposite to blue point. Okay, so there is no red to red. Okay, so that's the constraint. So you need to find the correct probability that's generate this type of permutation, and we want to generate this type of permutation efficiently, because the worst method in this type of permutation generation is by rejection. You know, because some of the like the likelihood of a certain type of occurrence is very slim. So if you generate all the permutation, which usually is n factorial, that's going to just eat up your RAM very quickly. So it's not even possible to generate everything. So you want to generate things just without rejection. So your algorithm always generate the proper thing, okay? But you can add some randomness because there are multiple multiple cases that's satisfying the solution at the same time. So of course you can find the AOPS link on this problem. It's AIME problem. Everything is documented on that. But we were going to show you how you program that in Wolfram language very soon. Okay, so let's just work on the random constrained permutation. First, let's assume there is 14 people. You always need they always need a even number, because for example, you take five people, like you put them on a regular pentagon. Well, there's no people sitting diametrically, okay? Because you connect two vertices of a regular pentagon, and none of them are going to pass the center of the circle. So you also have an even number, and we generate all the members. It's 1, 2, 3, 4, 5 to 14. And the key here is we need to first put people in the 7 diametric brackets. So before you put people on the seat, because we know so the proper seating is paired by a diametric thing. So you basically generate the diametric brackets first. Okay. So if man sit in 1, 8 must be a lady. So one lady. So it's red point, blue point, or red point, blue point. Okay. So these are the brackets that, because in that way, if you select 5 brackets out of 7, you always guarantee that there is only one man sitting in one bracket. And here is a quick comment about this problem. You can't have like more than half of the people are male, because by pigeonhole principle, if you say you have 8 people, 8 men, but you only have 7 brackets, so guaranteed there are at least one bracket with 2 red points or 2 males. So that will be 0 probability. Okay, you won't have anything like that happen properly or untrivially. Okay, so you always need have less than half of the population is male, and then you select a 5 of 7 brackets above. So what I say, and randomly choose one of the binary seating position, because binary seating is you can either choose 1 or 8, 2 or 9. So you choose a bracket and find the proper whether it's 1 or 2 or 1 or 8. Okay, so you do that, And once you put the 5 men in the brackets for all the women, you can just let them seat randomly. Okay, so that's the selection process. And then this thing comes to the visualization. You create a diametric link. So these links are just the dashed lines in our graph. Okay, and you link them, and that's, there you go. Then you have a graphics. That's, I probably need to increase the font. Okay. This gives you a proper seat arrangement for the problem. Okay, this one will generate the proper seating, and this is very important because as we progress, we'll see that the probability is very low for this type of seating to be available as the whole population grows up. So you always want to use something like this to generate the brackets first. So you guarantee always you generate a random permutation that satisfy the proper seatings. And then let's just create the diagram we see here. You just wrap up all the code, just copy everything we had before and put them in the table. Put them in a random function, so we can just run the whole things multiple times. Okay. So these are the 16 seats that's randomly generated, so we can have all the random permutations satisfy the diametric seating requirement. Okay, they all satisfied. Okay, there's no waste. I don't have anything to reject. So this is the most efficient algorithm to generate because, you know, nothing's get wasted. So this will generate very efficiently for even very large seating with like 400 people sit there. You can just do that without, you know, eat up all the RAMs in your computer. So it also works fine with like I think the most mainstream type of laptops. You have like 16 gigabytes RAM, 500 gigabytes of SSD, and i7 or i5 8th gen. After that, it's just, even for enormous numbers, this algorithm generate permutation with such a requirement on the fly. Okay, so that's everything we wrap it up for the AIME problem, because they just ask you about 15 or like small numbers. But we can go a little bit further to see how this problems evolves if we have lots of people, like 10,000 people. You know, what's going on? What's going to be the property that we are going to observe for really large input? So let's see. Say if we have 2n people and lambda n men. Lambda is a parameter because the most of the thing we have, for example, is the worst case we have is 100 men and 100 women. Okay, so it's fine to have 1 man and 199 women. Okay, because that will always give you the red-blue requirement we have in the problem. But so as n goes to very large, the maximum proportion of a man is n. You know, 1n over 2n is 50%. So that's why I choose the parameter looks like this. It's 2n and lambda n. And the lambda is to make sure the man is strictly less than half of the group. Okay, that's what we do here. So let's see the parameters, how the asymptotic things behaviors if we let n goes to infinity and have lambda here. Okay. Okay. So this gives you the asymptotic expression of the probability to have the required seating style. And let's simplify that. So this is the result. And let's see, so once you have asymptotics, you want to basically check that if the asymptotic expression gives you the same result as the brute force or direct computation. This is very important because for some of the problems, like typically in combinatorics, for example, if you want to compute n factorial, given 10,000, so 1 times 2 times 3 times, you go times 10,000. That's a really large number. Usually your computer cannot handle that. Even Mathematica can do that sometime, but if you do that, intensive computation, it just costs too much time. And you will always get overflow if you want to do direct computation for combinatorics with a large number. But I still want to know the behavior of n factorial if it goes really large. So I will use asymptotics to find a Stirling number for that. You can check on Wikipedia. It's very well known. It will give you a very simple expression to show the behavior in factorial. And we do same thing here, but for binomials and exponentials and binomials. So it will give you a very simple expression to compute that. Okay, so let's see, for example, let's fix n to 100 people and change lambda. So let's see how lambda, so this means like only 5% of the 5% divided by 2, that's 2.5% of people are male. These are like slightly close to 50% of people of the population are male. And if we increase n, if you fix n, we can see that as we increase the population of the male, the probability to generate the required seating style is vanishing very quickly. I need to just make it a little larger. You can see, somehow it's tiny here, but you can see that the number is 10 to the minus of 15. So this is on log plot. So this is means if you have, let's say, for example, 40% of 0.8 means 40% you need to divide it to. They're less than 10 to the power of negative 10 probability. That's you will need to find a proper seating. So it's just really not possible to do a direct computation and enumerate everything. But we can compare the result, the curve, with that from the direct computation. Okay, they look almost the same. Okay, you check at 0.8, it's still much less than 10 to the power of negative 10. So they match very well. So let's just can increase a little more. So if we just do some special cases. So if we have like 50% of people are male. So what's the result? Well, you get a much nicer expression for that case. So this is, as for example, if you have 100 people, you have like 10,000 people, and what's the probability that you find a seating with diametrically constrained with 50% of male? So and you take like 5,000, you immediately can tell the thing is on the magnitude 2 to the power of minus 5,000. Okay, you don't need to do any computation here, but you just plug in the number. Because that number is so tiny, you just take the logarithm of that to get the feeling of that number. So this number again decays very, very quickly. And so here's the difference between this graph and the previous one. So this one is a fixing number, but change the proportion of male and females. Okay, so this thing is fix the proportion, so like 50%, but change the number of population. Okay, and because it's 2n. Okay, so it's just uniquely determined by n. Okay, so we've specified the number of male, so the whole population is doubling that. So this is the result. And what's more important here is not about the actual expression here. You know, it really doesn't mean that much to me. But the thing is, it tells you that the proportion, the likelihood of such seating changes not only with respect to the proportion of men and the women, but also depends on the whole population. Okay, that's not something they asked during the AIME problem. You know, we once we do that, we would see this thing actually that's the key to understand the problem. Okay, so this also shows you this part shows you that as n increases, the estimate from our asymptotic behavior is very close to the direct computation. It's 8 of 10,000. Okay. Okay. So if this is also another special case is if you have a quarter of the group are male. So this is what you do, and you can have this expression, and you simplify that, and then you have that. And then if you go do more and more, you will find a very interesting expression is just 2 to the power of -5, 3 to the power of 3. And if you do that, you have more such things. But eventually you will find this thing is always less than 0. So this gives you the idea that eventually you will have something like some power to the power n, and some number to the power n. And this number is something generated by this, which is less than 1, because that's the logarithm of that number. It's negative, so it means that number is less than 1. That number determines regardless of what you kind of parameters you set for this problem, it always decays. It always decays very fast, like exponential. So, and this give you idea, but the different n of lambda will give you different decaying rate. So that's the key of asymptotic analysis in this problem. Okay, and then I have some. This is something like a half-life decay for this problem. What's the 50% chance for diametric seating if we have 200 people or 10,000 people? So. So for 200 people, let's just enumerate everything here. You will see that if we have 16 of them are male, we will have close to 50% of chance that you can generate the diametric seating. For if we increase to 1,000, the proportion of men must reduce to 2.7%. So that's the meaning of this calculation here. Okay. So with this software, you can do many interesting things to explore much more deep behind the problem. Okay, so that's I think a problem 1. We will split these things to couple sessions because I want to just let you understand very deep things about the problem. And just let me quickly look at the chat. Okay. Okay, I'm glad you like it. Okay, let's move to the second problems. Because most of the problems are independent. So once if we can split easily to multiple such live R&D sessions, if we don't have enough time to cover everything. And you have the notebook after the session, and also some of the notebook I will post on just separate them and put on individual blogs on Wolfram community. Just you have seen like this. It's published yesterday, so it's a nice one to read. It's such a simple problem that covers very diversity topics in combinatorics. It's just a great thing to have Wolfram language visualization tools. I just designed that diagram with some of the Wolfram function, repository function to make a very nice and informative thing to show what's behind this sort of puzzle. What's the solution? What's the idea behind the solution of the puzzle? Okay. So let's start with the second problem. It's a problem from PROMYS, but because internet is so big, okay, and social media like AOPS and even on TikTok, people start to share math problem solving. So you easily have duplicates. So if you see enough, you probably will encounter the same problem in different competition or different selection sections. So this is a very interesting problem from PROMYS 2023 and the Bangladesh MO 2001. I saw that first on Michael Penn's channel. He talked about that. I think it's a fun problem. And it's if you also search repeating integers on MSE Mathematica Stack Exchange, you will see this problem as well. But we will give you a general way to generate such a sufficient condition to generate lots of ridiculous things. Okay, so so how many positive integers can you find? Okay, they're actually infinity, but we pretend we don't know the solution yet. Okay, so for what I've said is discrete or number theory stuff. You always do that by testing the numbers. Okay. You do that by 2023 and 2023. Okay, it's of course this function is not necessary. Okay, I just find on MSE in case I need it, but I find I can skip that in the problem. So it means, but just give you a good name, perfect square cube. Okay. Is it a perfect square cube? It's not. Okay, you do that, you just take the square root. It's not integer. That means it's not. Okay, so what the equal means here is quite obvious. You just repeat the number in the connected. You go 11 is a 11 equal number. Okay, 1 1. 22 is you have 2 2. Okay, so you generate all the 2-digit stuff. So of course, just like the previous problem, we only need a someone asked the best way to learn Wolfram language for solving math problem. Just follow this channel, I think. I actually answered like 300 problems on AOPS before with Wolfram language. So if you're lucky to find me, so you will see you can start from reading those solutions. So this gives you it's kind of silly, just repeat this numbers. In the previous number, we will say the number of the population must be even. The same case here because you duplicate a number. All right, so you must have even digits. You must have even digits. Okay, 1 1 2 2 3 3 4 4 8 8 9 9. Okay, and then you do that for 10. This is 4 digits. Okay, 4 digits. 4 digits. 1010 11 12 12 13 13 14 14. Okay, so you test everything. Okay, the easy way to do that is just let me just define this one again. Here we go. The union false. Okay, if you have anything like true, it will just give you true. So everything is false. It's just you union all the solutions. You find the union of all the solutions, and it is false. Okay, so it's false. Okay, so which means it's not possible to do that with such type of thing. If you are exam takers, it's not possible for you to test 999 to like even 10,000 number. Let's do that again for even more because Mathematica Wolfram can handle more numbers. So 100 that's 6 digits. Okay, 6 digits. You do that, it's a false again. So none of them are false. None of them give you a perfect square, and then you do that. And if you conclude that thing, if you conclude, you test a million number and none of them are right, you feel like, well, it's probably nothing exists. But very obviously that if you plug this numbers in the calculator, you repeat that number and take the square root of that number. So let me just show you how to type this number. Command C. Okay. You delete it, copy. It is integer. You see, this shows you this number is a perfect square. And if you don't believe me, you can just take this let this guy times itself. See, this is the exact number you have. You can just compare that and digit by digit, and then so this is number obviously. So at least you can find one. You know, it's quite obvious because you can test it directly from the calculator. So let's see how you find this number. There are a couple of steps because first is that you need to generate some numbers. You know, just find some numbers that probably would be candidate, but by looking at the way I generated this number. So it's I times by 1001. Okay. So if you do that incrementally, you know, by checking if like this number and by 102 or something like that, you will probably won't have enough time to find it in your lifetime. So we will need some smarter way to do that. Is we factor this number. We factor this number. The key is if you have say this number, okay, for 4 digits. This is 4 digits. It's AB times 101. So you must have 101 is a factor of AB, which is not possible here, okay? Because you want this number to be perfect square. So 101 is a prime number. You need a 101 in AB for it to work, okay? So what if 1 something 0 1 is not a square? Is not a prime. So for example, these guys are not primes. Not primes. You know, you can find a factorization for that. Okay, but none of them work. You can just test it. The issue is that everything above this guy and number 11 before this guy, you always have factors, prime factors with at most power equal to 1. Okay, so that's the tricky part. So the idea here is if you want to generate a thing that can be perfect square as you repeat part of that. For example, with this guy, so this is this guy. You need some factors to be have even power, because this guy won't affect the perfect squareness of this number. You for example, you have 16, you divide by 4. 4 is perfect square. So 4 left is also perfect square, right? So you get rid of a perfect square, that should be fine. And then you need you have these things. And because these things, when you multiply together, will have less digits than this number. So it is possible for the product of this number as a factor of this guy. Okay, so this is how we find it. And then you take that thing out and you keep all the factors here. Okay, but these factors are not enough, because if this number only have these factors, you can just multiply that thing out. You won't have 11 digits. So we need to put some numbers for that to make the 11 digits. So what we do here is we need to do some calculation and find the right one. Okay, so this number times 7 squared is 11 digits. Okay. So you may ask why don't we multiply anything like a 12 to that number? Or maybe, for example, it's 48 to that number. Okay, make sure this number times this number must be perfect square. So you have to keep this part and multiplicate a perfect square to have the proper candidate. Okay, that's the idea. So if we choose 7 here and multiply 5 here, and 5 works. So let's just take it out this number. And let it times the 10 to the power 11 plus 1, and to find if it's a perfect square. It is. You just take a square root of this guy, and that's the result. So this guy times this guy is a perfect square. Okay, so you, which means you repeat this number. They repeat this number. Repeat this number, and take the square root, and you multiply this guy. It is the square root, integer square root of the number. Okay. So can we make the code a little better? Yes, we can. Because with this code, we are not good enough to find this guy. This is way beyond the factor integer stuff in general. So we need to find a better way. So this step 2 is a better way to write the code. It may just make it look fancier, but it won't handle that large number. It's a number theoretical function called Mobius mu. I'm not going to explain too much here, but it's very well used in analytic number theory. It's basically test the square freeness of algorithms of a number. For example, 12 will result 0 because 12 is a 2 times 2 times 3. You have a power 2. You have a power 2 of 2 of power 2. So it won't give you anything non-trivial. For non-trivial stuff, you have 15 is non-trivial. 15 is 3 times 5. 3 times 5 is 1 3 and 1 5. It gives you 1. Let's see. 30 is non-trivial. 30 is 2 times 3 times 5. You have 3 distinct prime factors, so it gives you -1. So if you have odd number of prime factors, you have -1. You have even numbers, it gives you positive 1. If you happen to have anything like 2 4 in the factor, it gives you 0. Okay, anything like 25 is 0. Okay, so basically that's what it is. It sounds simple, but it's NP hard. There's no efficient way to do that. If you find that one, you get maybe Fields medalist for that. Okay, so this guy gives a 0 because we have 11 to the power 2 here, so it's expected. So basically, it asks you you need to find the things result 0. Okay, yeah, there is another function you can use. Is a square freeness Q. Square free Q in mathematics. So this basically does the same thing here. Let me run that again. So even see 50 is really slow. So 11, 21, 33, 39. So 39 is a candidate. So this guy is a candidate, and you do the same thing. And because the 13 is 13 square is the square. So we find any perfect square for up to times the leftovers, and give you, oh my god, this is give you like 13 give you 39 digits. So basically this is how you do that thing. So it's the same thing. That's the number you can test. It's a perfect square. For even larger numbers, well, why the solution was obvious is because we use number theory stuff again here. So there's a interesting thing that you can check in the factorization is even though the number itself is really not that big, but you do have very large prime factors occurs very early because, for example, there are a bunch of more prime factors. Let's see, 19, for example, is much less than this guy, but 19, okay, let's do a little bit more. 73, 77, 37, for example, 37 is I would say 37, not 73. Okay, 37 is a much smaller one, but does not occur. The reason is this guy actually gives you very small number in terms of multiplicative order. Okay, let's make it in the graph. say 10. Let's see, what's the prime again? This guy. Yeah, it's 24. It's really small. So, which means if you have 10 to the power of 24 mod, you basically divide that number. It gives 1. Okay. The other question is when something like this have as a candidate with 9, so basically means that this thing is 2. So what time when it's going to be 2? So that will be a little bit more difficult because that number probably occur very late. So we have that. This means 10 to the power of this guy. Oh, sorry. This should be minus 1. Oh, it's 12. It's 12. Okay. So so when we have something like this with this guy, which becomes 2, so it contains the factor like this, we make it 2. So let's do that. Square. Okay, it probably takes some time to find it, but that's the idea, to find the integers that satisfy this condition. So this is basically how you find some ridiculous number to handle that. So let me quickly explain the multiplicative order here used here. So in this case, for 11, okay, let's do that, minus 1. So 10 to the 11. So this guy means 11 will work in this case. 11 will work. So you have 2. Okay, so it is basically let you to solve residual families that satisfy a certain condition. For instance, 10 to the power 10 mod. This thing basically means what kind of number you can find for 10 to the power of x such that when the mod 17 it is minus 1. So basically they need to ask you to find x, but there are multiple x like that. For example, if you say you have like a 4, so give you the minus 1, okay, but of course 12 will make sense because that's minus 1 times minus 1 times minus 1, so minus 1 to the power 3. So you ask to find the minimum x that satisfy this condition. So let's take a look at it. This is like 8. Where 8 comes from is you do that. Okay, you take 10 to the power of 0 to the power 1 and to the power 8, and eventually you will have this guy. So why this is a minus 8? Because minus 1 occurs at 8th position of the list. The reason is very, much more difficult to is way beyond the if you have like higher order of 17, like p to the power more, it's p-adic numbers. It's I actually wrote a blog about that. So you can, if you have you are interested, you can read that. It's how p-adic number affects our solution seeking process. So this is basically gives you an idea how you find the power over k that works. So in this case is if we have 11 to the power of 2, it will give you 10 to the power 11 mod this guy equal to minus 1. So which means you will have these guys always work. Well, why you have k times 22 not instead 11? Because 22 is 1. So 10 to the power 11 is minus 1. So 10 to the power of 22 is positive 1. So this guy times positive 1 won't affect its modular result from 11 to the power 2. The other thing I want to point out is sometimes you cannot find a multiplicative order. It just give you something like this. Because, for example, 10 to the, you look for 10 to the power of a 0 and a 1, because you only have 2 options here, right? None of them will give you for example, 10 divided by 2, just with modulus, for example, minus 1. So it's not possible because 10 is 2 times 5. Regardless of how you do that, it's always gives you 0. You won't have a multiplicative inverse in this situation. So that's why the algorithm is very efficient to find the proper result, because we directly look at the solution, the pattern of the solution, in a higher level. And these things are equivalent. Coprime false and these are false. False, false, and unevaluated. These 3 results are identical in my case. So the ridiculous number I'm looking for is just to plug in k equal to 16. It gives you the result. And you do that, you can just find the integer factors of that number and repeat it and do the test again. So you will have the result we have in the list. Okay, that's the equal of integers. Okay, this is my remark. Okay, so this is how you find the even larger number. Oh, okay, I use this one. It's much smaller than the one causing problem. So this number works. Is also a good candidate. So if 10, you can find a modular multiplicative inverse of this guy, and you plug this guy in here. This is a valid candidate, not for the solution, but it's a valid candidate for these guys. Because first you need to find these ones, some 0, 1 things before you can move on to find the solution. So this number is way beyond any machine you can handle on Earth. I mean, the number of all the atoms in the universe combined, comparing to this number, is a joke. Okay. So there's no way. But with the number theoretic thinking, we can confirm this number works. Okay. So this is the power of the number theory. Yeah. To understand this type of problem, probably you want to get familiar with a modular arithmetics first. I think Wolfram language give you very nice functions, coprime and the GCD stuff, everything you can work with large numbers very easily. And this is the foundation of cryptography. If we have another things scheduled, I think I'm just being comfortable to talk about cryptography with the built-in functions. That'd be very nice to show you the power of number theory in real life. Okay. The third problem is from PROMYS. It's a kind of long one because I think these things require not only you have good math capability, but you also have good reading capability and writing skills. Okay, so you need to present your solutions very nicely. So this problem is basically ask you, you have a list of train on the track, and there's no overtaking. Okay, so for example, you have a slow train and a fast train moving from left to right. Okay, you're moving left to right. So from left to right. Okay. So if the fast train is on the right, the slow train is on the right, fast train is on the right, and the slow train is on the left. Everything is travel to the right. Okay. You will have two chain of trains because the slow ones will never catch up with the fast one. But if you reverse the order, put the fast train on the left and the slow train on the right. So eventually there is going to be a collision, but the collision is not a real world collision because it won't cause any trouble. But the only consequence is the two trains will travel at the same speed as the slow train. Okay, what I mean? So let's see. If there are three equally spaced trains that give you different speed. So for example, they travel at 1, 2, 3. Okay, so 1 is on the left, 3 is on the right. So eventually you will have 3 trains. Okay, 3 chain of trains. So it's and one chain can be only with one element. So that's the eventual case. But if you have say 3, 2, 1, 3, 2, 1. Okay, you travel to the right. So eventually you will have one chain because 3 hit 2, for example, and they all travel at 2. 2 hit 1. You eventually hit everything becomes 1. That's the slow train. But what about 3 1, 3, 2? 1, 3, 2. 1, 3, 2 is 1 is really slow on the left, but the 3 will catch up with 2. So eventually you have 2 trains, right? 2 chain of trains. So they ask you what's the average of all possible orderings, So basically, if you have 4 trains, you have different permutations, right? And different permutation or different initial state determines the number of trains you have eventually. So let's see how we can solve this problem with the simulations. I did not solve it at the beginning, but but once I have the code, I generate some cases and throw it into Wolfram Alpha to give me a solution. So even sometimes people preparing for this type of exams, they spend too much time on a single problem. And that's bad because for discrete calculus number theory, you want to see more problem as many as possible. So don't spend too much time on that one problem. And its reading solution is also a very important part of the learning process, and more importantly, understanding the solutions, okay, and finding connections. And this problem gives you everything like that. Okay, so if you learn anything like programming, for this type of problem and for very long chains, you want to break into subproblems. So it's either divide, conquer. So as like a recursion, you solve, for example, you want to know Fibonacci number at nth place. You basically computed the 2 numbers before that, and then 2 numbers before each of them. So this divide and conquer. Or you can do like dynamic programming because it's not only divide and conquer. You also save the result from your previous subproblems. So eventually, you don't need to do the subproblems again. So you can just use the result from them. So this problem is kind of similar. So if you try to do that but because though they only ask you like 3, 4, 5, 7, but if you are anyone like interested in math, you easily think about how we do that for 10, 20, or even larger number of n. It's the nature of these math lovers. So I think you have a program language, like a Wolfram language, that really helps you to understand this very quickly. So the key is the problem is so what we can think about easily is if you have 1 on the left on the rightmost side, so everything is going to be one chain because even slower, some slightly faster train, they collide together, they will be the slowest one, but slowest one is at least 2. So you will have so eventually everything will catch up to if for example you have something 3 in the middle, but 3 will catch up with 1, and everything becomes 1. And you have some, leftovers. Eventually, they will catch up again with the leftovers because the rightmost chain, because the rightmost chain will be the slowest one at speed of 1. Okay. So if it's quite obvious. If 1 is on the right, eventually you have only 1 chain. Okay, that's the extreme case. But how can we extrapolate the extreme case to the leftovers? Could more cases. So we will think about it. We have used up 1. So what about the others? Because if we get rid of the slow things about some of the part of the trains, the slowest train for the leftovers will be 1. Okay, because it's quite obvious, So that gives you idea about the induction. Okay, so if we extrapolate the thinking it's not about the actual point, the actual number of 1. It's about the slowest number, the smallest number for any leftover train, and it's 1. Okay, it's the new 1 of it because this is if we talk about like abstract ideas, it's like a countable set. Finite accountable set. You always have a minimum value, and that minimum value will automatically becomes 1 if you take the slow trains out. Okay, so that gives the idea to create a very simple program. It's not necessarily the code golf thing, but I think it's just simple enough to give you an idea what's going on here. So the key is, if we have an empty train, we have 0 train as 0 chain. And sometimes we'll also have 1 chain. So 1 chain, for example, if we have every number available, say like 1, 2, 3, 4, if 1 is to the right, then you will have 1 chain. Okay, but what if 1 is not available? What one is not available here is you need something like 1. So what is 1 for something like 2, 4, 3, 5? So 2 is 1. Okay, so 2 is 1. It must be on the rightmost hand side. Then it's the slowest one. Then you eventually have 1 chain. So that what it means is if you have the minimum number on the rightmost hand side of the list, you have 1 chain. Okay, and then we do recursive thing is we need to find where the smallest number in the list, and that number will break the chain into 2 parts. One is something like, for example, if we have 6, 4, 1, 3, 5. Let's just write it down. 6, 4, 1, 2, 3. Okay, 1 is in the middle, so this guy would be something like a 1 chain or something, right? And this will be another thing. Okay, and then you call it again because this guy is the smallest number. It's on the left, and it break it into 2 chains. So eventually you have 1. This. So basically, it will turns to 1, 2, 3, and you eventually have 3 chains of trains. And then you do that. You can just use the code to do some test. It generate cases for simple cases quickly. And what if we do 3 case for 10 numbers? It'll give you 3 chains. So this guy would be 1 chain, and this guy would be 1 chain, because 9 hit 3 would be 3, and 5 catch up with 3 becomes 3, and this guy is everything eventually becomes 1. So this is 1 chain, and 2 is itself, and this is 1 chain. So eventually you have 3. Okay. We can also work on really large numbers, and like I found, it will give you some numbers. You can just quickly check that. And then how to find the averages? I just do brute force for small numbers. Oh, okay. Let me just pause that. Or define everything first. Clear. Let's gonna do some smaller numbers here. Okay. Rest to give us an idea. That's the distribution of the number. It doesn't look very. It gives us a general idea about how the number behaves, but it does not give you the actual solution for that. Let's see. Rest is. Look at rest. Okay. Oh, that's all the result here. Let's just do that again for the permutations, for all the permutations for 1 train, 2 train, 3 trains, 3 train, 4 train, and 6 trains together. Okay, then you have a list of numbers, and that's all the sort of the possible outcomes. The outcomes, and I'll just ask a number, throw that online, and I find it's this number. So ask Wolfram Alpha, exactly the same. It's this number. Either on OEIS or Wolfram Alpha will give using the same idea. Give you an idea. And what I mean is for connections is if you happen to find this number is a famous number, then you're good to go. Because this number, you will find tons of literatures about that on OEIS or MathWorld. So it will show you why this number works, why this number is associated to our train counting problems. So if you, because there are the certain number here is not that general. It's required this guy to be 2. You use the parameter set it to 2. It will give you the proper result. So 1, 3, 11, 50, 274, and 1764, and so on. And it happens to be the n-factorial times harmonic number. So the average number is this number divides the harmonic stuff, divides n-factorial. So what you left is harmonic number. So that's the average of the length of the train. You can do that. That should be the same thing as our result. You can 761 over 280. 761 over 280 for 8 trains. So this will give you the solution for that. And what's more importantly here is the average actually diverges, right? Because this is a well-known property of harmonic numbers. It diverges very slowly at the rate of a log n, but it diverges. So that's something you can learn from. You can immediately point out for the problems. And then, just as I said, if you happen to find this is a famous number, then you have infinity resources to learn the connection of Stirling numbers, harmonic numbers, and the number of trains we are counting that. So yeah, I think if you just do that by hand, I think it's pretty time consuming to find anything useful. And even if I have like a number like this, it's not a arithmetic progression, or it's not a simple like a power or geometric result, geometrical progression. I think I probably have hard time to find out what's the number going. I'm not Euler or Lagrange, so I need some technology to help me. So eventually I find out that this is the result we are looking for. So yeah, it's you can find the link from OEIS. You just Google it, or you use MathWorld to find tons of reference about why this number work. And typically, I think this relates to this problem because this Stirling number S is originally associated with the number of distinct partition of cycles in the chain of integers. So that makes it sound like very close to our train problems. So yeah, I think that's it. I still have a couple more problems, but I think it would be good if we take a break today and talk about in the next part of the problem solving session. And hopefully you learned something very useful today, and see you next time. Bye-bye.